So we are discussing the hydrogenation reactions, and then two types of hydrogenation catalysts are possible. One is this monohydride catalyst, another is this dihydride catalyst. Monohydride catalysts are the one which you see over here. It has one hydride to start with. Okay, dihydride catalysts are the one where actually zero hydrides are there. So monohydride will have one hydride, dihydride will have no hydride. For example, here this is a monohydride catalyst. You have one hydride to start with. Of course, both the monohydride as well as dihydride will give the hydrogenation product. For example, olefin you start with, you get an alkane, right? Now you have seen for the monohydride catalyst in the last class, there is this 18 electron species goes to 16, goes to 18, back to 16, and then back to 18, back to 16. All these are absolutely necessary that we have discussed. Why anything else will not be possible also that we have discussed. That is because if you do anything else, this reaction will not proceed in the forward sense. And of course, the electron richness of the center will also be another important issue to consider for oxidative addition. Now for the dihydride catalyst, well, we did not correct it yet. PPH3, this was either you can take Wilkinson catalyst or Strock-Osborne catalyst and or Cabtridge catalyst. This is the most used one, Wilkinson catalyst, which is a very common one, not so expensive one. Strock-Osborne catalyst as well as Cabtridge catalyst has these alkene, which are sacrificial, ligand or substrate, because it will fall off from the catalytic cycle. It will hydrogenate because we are dealing with an hydrogenation catalyst, and these unit will undergo hydrogenation before your main hydrogenation reaction even comes into picture. So these are sacrificial one, but it gives the right opportunity to add your very difficult olefin, which is otherwise very near impossible to hydrogenate. Well, let's moving on. For this Wilkinson catalyst, we have a very simple intermediate, which is a 16 electron species, goes to 14 electron species after losing the phosphine, and then oxidative addition will take place. Once again, why oxidative addition over here, not olefin coordination? That becomes very clear because we have a relatively electron rich species, and olefination is not going to be helpful at this stage. So we have a 16 electron species, and then olefination will lead to the 18 electron species, and then beta migratory insertion leads to 16 electron species, and then reductive elimination goes to the 14 electron species. Overall, if you compare the monohydride catalyst and dihydride catalyst, there are subtle difference where the oxidative addition takes place, where the olefin binding takes place. Here, as you can see, ligand dissociation is common, then oxidative addition, then olefin binding. Of course, beta migratory insertion, reductive elimination are common. So oxidative addition, then alkene coordination. As you have seen in the other case, first alkene coordination, then oxidative addition happens. Of course, these are finer details, but overall, all of these will give rise to the alkane product, olefin to alkane product. For instance, you have a olefin here. How do you know that what is the mode of addition? Let's say you take this sort of cis olefin, you can add D2 or deuterated hydrogen or D2 with Wilkinson catalyst. What we'll see, you will get only one diastereomer. This is exciting. You get only one diastereomer. These are not trans addition, these are cis addition. This kind of nails it. By proton NMR, you can very convincingly prove that this is what is happening. Indeed, experimentally, that is what is observed. In the 2 slides back, we have briefly showed you the Cabtridge catalyst and Strock-Osborne catalyst. We can go back again here. See, this is the Strock-Osborne catalyst, which is a rhodium-based. Cabtridge catalyst is iridium-based, PCOI3 and pyridine as a ligand, and here PPH3 and PPH3 as a ligand. And nonetheless, in these cases, what you see that both of these cases we have a 1+ complex, right? 1+ complex, which is the chemistry is happening. And as I was also discussing, that this would lead to a point where olefin coordination will take place at this phase, which would be very important for this sort of reaction. Can you see my slide?
Yes.
Okay, no problem.
Perfectly
right?
all right. Yeah.
Okay, sure.
Fine.
So the Strock-Osborne catalysts, as you have seen, Crabtree catalyst versus Strock-Osborne catalyst. Crabtree catalyst has iridium in it, and you have seen the ligands. Ligand is of course two olefin ligand which will fall off, and then there was this pyridine ligand and phosphine ligands, right? So phosphine ligand and pyridine ligand from the Crabtree catalyst. So this little bit difference is there, but these two complex, this one and that one, these two are the Strock-Osborne and Crabtree. These two are the one which is really effective for the hydrogenation catalyst. Usually if you have non-substituted olefin, I think you would not be, or mono-substituted olefin, you don't have to use Strock-Osborne catalyst or Crabtree catalyst, because simple any hydrogenation catalyst will be effective. For example, Wilkinson catalyst will be good enough. But when you have bulky or substituted olefin, then the problem happens, you don't see any product at all, zero. I mean, you don't see the product formation, and that is because the olefin cannot usually bind with the metal center. Well, this is where the Strock-Osborne catalyst and Crabtree catalyst comes into picture, because their coordination number is 2 only, although it starts with 4, but it loses those 2 olefin coordinations, and that makes it 2 olefin coordination. So it's a bidentate ligand or bidentate system. You can see pretty less crowded system. That makes it very easy to react with simple di or tri or tetra substituted olefin, because olefin can now coordinate with this metal very effectively. Okay, steric bulk is out of question. These are positively charged, as you can see, positively charged species. Both of them are positively charged species, and they can interact with the metal center. Olefin can interact with the metal center pretty effectively, because it's the sigma bonding has to be really effective. Okay, or the olefin donation to the metal center is effective because of the cationic charge, and this make it very effective for olefin binding, and the hydrogenation reactions proceeds. As I was saying, norbornene and cyclooctadiene, which is they are in the starting material, this can act as a sacrificial ligand. That means this falls off during the catalytic cycle. These do not have any other role in the catalytic cycle. Okay, they are just providing the support, falling off. They don't participate in the main catalytic reactions. Okay. Now, as I was discussing, there are different ways you can get rid of different group, and these are the different means. If you have an alkene associated with metal, you want to do hydrogenation. If you have CO, you want to use light. If you have an hydride, you want to use this cation, bulky cation. If you have an halide, you want to get rid of, you use silver nitrate or silver salt. If you have an alkyl group, let's say MR group, if you have organometallic complex, you want to get rid of this R group, you can use the H plus or proton. So that's how you get rid of. So MR goes to M if you are using protonation technique. Of course, you have to choose the right condition, right solvent, right protonating source, but it's technically it is possible to go to ligand metal R complex to ligand metal complex by protonating it. Okay, moving on. So for the Strock-Osborne catalyst, as I was telling you, the main important thing is the low coordinated metal complex. That means the counting of electron will be also very low, and it's a cationic species. So the olefin, even if it is very bulky, let's say tetra substituted one, it still can bind with the metal center pretty effectively. It becomes a 14 electron species, 12 electron species becomes 14 electron species. Olefin coordination is pretty easy, and then usually it is found that since for a 14 electron species it's not really a very electron rich system, we see that oxidative addition, that means addition into the hydrogen sigma bond, hydrogen sigma bond, this becomes the rate limiting step. Okay, this becomes the rate limiting step. From here, beta migratory insertion takes place to give the metal alkyl intermediate. From there, after beta migratory insertion, you undergo reductive elimination to get the product. Okay, just to go back and simply to show you, you have 12 electron species, then a 14 electron species, then a 16 electron species, then back to 14, and then back to 12. So olefin coordination increases the ligand counting or the electron counting 12 to 14. 14 to 16 electron again binding, olefin binding increases the ligand count, and then 16 to 14 again happens pretty effectively due to the beta migratory insertion, and then reductive elimination gives the product formation. Fantastic. So that's very simple. This is similar to what you have seen in the hydrogenation reaction, as I mentioned. Whether olefin coordination occurs first or oxidative addition, these are the two steps you have to look out for when you are looking for the mechanism of this reaction. And these beta migratory insertion as well as reductive elimination is pretty common, or very easy to happen. All right, moving on. So we then can go for the stereoselective hydrogenation reactions. Stereoselective hydrogenation reactions are essential part of synthetic chemistry, both in industry as well as in academia. There are plenty of molecules where you need to generate a stereo center. So for example, this is a medicine, right? L-DOPA, treatment of Parkinson's disease or other many different medicines use L-DOPA is used, right? L-DOPA synthesis is one of the crucial synthetic steps, right? And well, L-DOPA, such an important pharmaceuticals which is really sold worldwide in a huge quantity. This L-DOPA as drug can be prepared from this corresponding olefin. So we are taking an olefin and we are basically hydrogenating it to make it alkane, but in an asymmetric fashion. So this is the new chiral center getting generated. Of course, you need to take a chiral ligand, which is taken over here, as you can see. So the chiral ligand induces chirality in the achiral substrate. So due to this chiral center, this rhodium complex, again the rhodium complex, it's like similar to your Strock-Osborne catalysis, right? You have a bidentate ligand, it's a Strock-Osborne type of catalysis, bidentate ligand which is chiral, and now giving the chiral center. Fantastic, simple ligand, simple reactions, but very effective reaction. This reaction or these sort of reactions are done industrially in metric ton scale. These are like really effective reactions. Here is another one, aspartame synthesis. As you know, aspartame is another very important molecule as sweetener. Aspartame is used in quite large quantity. This can be also done in pretty effectively. Similar ligand as previously used. We can use L-aspartame and hydrogenate this olefin to get a very high enantiomer selectivity of this sort of reaction. So choice of phosphine ligand, which are the chiral ligand, as you have seen in the other case, is critical and very important which sort of ligand we are using. But overall, this olefin, as you can see, going to alkane, and a new stereogenic center is generated right over here, which determines the stereochemistry at the point where the ligand, this ligand on the rhodium will dictate the stereochemistry at this point, right? What is going to be, whether it is going to be R center or S, that will be dictated by the ligand for the metal center. But overall, otherwise, this is a simple hydrogenation reaction, Strock-Osborne type of catalysis. As you remember, the mechanism will be something like this. Simple mechanism, olefin coordination, oxidative addition, beta migratory insertion, and reductive elimination would give rise to these product formations. Okay. So moving on, there are quite a number of interesting asymmetric transformation or Diastereo selective hydrogenation reactions are feasible. For instance, here you start with a chiral center into the molecule anyway, right? This is a chiral center. Now this is an allylic alcohol. You look at it, this is an allylic alcohol. Hydroxy group is above the plane. Okay, hydroxy group is above the plane. Now in this case you can take a Strock-Osborne catalyst or a Crabtree's type of catalyst. What happens, you get the dihydride addition. As I said, always hydride additions or the hydrogenation is from the same plane or the cis. So dihydrogen addition or dihydride addition, it is happening from the same plane, above the plane. In this case, this hydroxy group is dictating the term. This hydroxy group is dictating the term to direct it to do this reaction at a particular point, right? As you can see, this hydroxy group is giving you the product where hydride is top, and then we have this product. So in this product you see two stereogenic center now, right? Just go back. If you come back here, you see that you started with one stereo center containing molecule and you end up getting two stereo center, one stereo center here, another stereo center there. Of course, these are going to be a Diastereo selective synthesis, and the diastereomeric ratio is pretty high. The hydroxy group actually directs the hydrogenation reaction from the same plane as the hydroxy group is. If this hydroxy group was below the plane, since this is above the plane, the dihydride or hydrogen addition is happening from top of the plane, and hydroxy group in these cases is acting as a directing group, directing the hydrogenation reactions. On the other hand, if you take a allyl alcohol, as is this one, which is now then protected, the same allyl alcohol, but then you protect it with a protecting group, let's say silyl tertiary butyl. Now this is no longer a directing group. This is a bulky group now. It cannot bind with the metal center because it was hydroxo and less bulky. It was directing or it was binding with the metal center, and then that further was giving the direction where the reaction would be happening. In this case, what happens, this is not the case anymore, and we have this protecting group which is becoming very bulky. This is a then disubstituted bulky olefin, and then you see the hydrogenation reaction is now happening from below the plane. So this is the hydride, this is the hydride, 2 hydrogen is coming from below the plane, as you can see. As you can see, it is happening from below the plane. Previously, it was happening from above the plane. Okay, I'll explain it a little bit slowly once again. So hydroxy group, as you see in this top case, hydroxy group is here. Now this is binding with the metal, and that directs that hydrogen addition are from the top. As you have seen with the deuterium leveling, both the deuterium was adding from same plane. In this case also, both the hydride is attaching from the same plane, top, because hydroxy group is directing which phase it is going to be accessible for hydride addition. Fine. Now when you have hydroxo group is no longer hydroxo, it is protected, then this is no longer attaching with metal. So this metal binding is not happening. This becoming a bulky group, this whole thing become bulky group. Now since it's a bulky group, an olefin is coordinating with metal center, from the same phase where bulky substituent is there, hydride can no longer attach from there. Okay, and also this metal is not really attaching with this. Okay, so this is when you see we are seeing that this reaction is happening from the from the same in a different plane as it was happening in the previous cases, right? So once again, so Mamta, you are here.
Yes, sir.
Okay.
I was disconnected for a while, just
Okay,
for a
no
second.
problem. No problem. No problem. So we are seeing that once the hydroxyl group is above the plane, the hydride addition is happening above the plane. If the hydroxyl group is below the plane, hydride addition will be happening from the below the plane. Okay. Now, how will you get the other diastereomer? Well, for that, you can just simply protect the hydroxy group, and then it becomes a bulky group. The hydride addition happens from the below the plane. So this hydride and this hydride happening from below the plane, because top of the plane is really blocked by a bulky group. So this is how, if you look at these two compounds, actually are now two different diastereomer from the same starting material. You start with the same material, same starting material. Now you get two different diastereomer, which is quite fascinating. Okay, which is quite interesting, and both the products could be of immense importance in synthetically, both in industry as well as academia. So both Strock-Osborne catalyst as well as Crabtree's catalyst are used for directed, while Wilkinson catalyst is used for usually non-directed hydrogenation reactions. Okay. Okay. If there is any question, I'll be happy to answer. Please go ahead and ask any question that you may have.
Sir, other than Wilkinson catalyst, both the catalysts that I cannot
Strock-Osborne,
spell
yeah.
it. Yeah. In
Strock-Osborne and
both the
Crabtree.
catalysts, they have the PF6 based.
Yes.
So why they choose this? Because of the big size or any surface chemistry regarding this?
Yeah, I can discuss that. So what you see here, of course, as I was saying, my drawing is a little bit incorrect here. I will correct it once more. So this was this was trisphosphine,
Right. Yeah.
3 phosphine ligand and 1 chloride. This chloride ligand makes sure that this rhodium is not really that much positively charged. Okay, this is like neutralized. Positive charge of rhodium is neutralized by chloride, right? So what happens then, if you have a bulky olefin or less electron rich olefin, this sort of olefin, let's say tetra substituted olefin like methyl, completely substituted, just I'm giving an example. If you have olefin like this, it will not be able to attach it. Why? That is because number one, it is very crowded with 3 phosphine ligand or at least 2 phosphine ligand, bulky ligands are there. Okay. Second of all, there is this rhodium is not really positively charged. Although rhodium is 1 plus in all the cases, or at least in both the cases, here also plus, but this charge, chloride, is neutralizing, which is in the the primary coordination sphere, and it is coordinating with rhodium. So the charge of rhodium is getting neutralized effectively, right? On the other hand, if you add PF6, it is a non-coordinating anion, right? It does not coordinate with the metal center directly. It's a counter anion, right? It is outside. So that leaves the rhodium 1 plus, both of them are 1 plus. This 1 plus is much more effective 1 plus than this rhodium in the Wilkinson catalyst, right? So what I'm saying is this rhodium in Wilkinson catalyst is not that cationic, but although being the same rhodium 1 plus, this rhodium is really cationic, very, very cationic. And that makes the olefin coordination easy. Now, why PF6? That is because PF6 makes it, of course, solubility is one of the issue. So PF6 will make it soluble in, let's say, acetonitrile or some other methanol, acetonitrile, this sort of thing. And more importantly, I would say this is a non-coordinating one. We don't take here a chloride or bromide or other coordinating anion, which will create a addition at the rhodium center directly. We don't want to add at the rhodium. We want a counter anion, and that's why PF6 is taken. Of course, you can take other so-called BPH4 or BARF or BC6F5 1 or BPH4 1 or B that C6F5 one of the BARF, okay, 4, and bulky anionic bulky, which are counter anion, big counter anion, does not really bother too much of the reaction in the coordination sphere. So PF6 is not absolutely necessary, but it is also cheaper, compared to any of these other one, BPH4, BPF6. So this is cheaper, readily available. I mean, perchlorate could be another one, but as you know, perchlorate could be a little bit explosive, right? So considering all those things, and also you are talking about the commercial availability, cost of the starting materials and everything, right? So all these things comes into picture. I would say, let's say, readily availability, which is available, cost of the counter anion, which is, so for example, BC6F5 or the boron, a big one, 13246 trifluoromethyl one. I'm not drawing it properly. It's called bar for bar prime, whatever it is, the big one, counter anion, boron tetra substituted one. Those are the ones which are very expensive one, prohibitively expensive, even much more expensive than the rhodium or iridium itself. So the cost, ready availability, solubility will not be a problem with the BARF and many others, but even they actually will be much more soluble. If you take at the BARF one, BC6F5 or this benzene ring containing one, tetraphenyl BARF one, those are even actually much more soluble. But again, depends what you want to do. You keep on modifying it. The major reason, as I said, that these are non-coordinating. This does not coordinate with rhodium or iridium. That makes it easier for the chemistry that we are looking at. Otherwise, it doesn't work. If you have something like chloride attached with it, the difficult olefin, like disubstituted, trisubstituted olefin, will not undergo hydrogenation. Okay, because they will not be able to even coordinate with the metal center effectively. As you are seeing, coordination in every mechanism, whatever mechanism you look at, coordination of olefin has to be there. Without coordinating with the metal center, you will not able to do this reaction effectively, right? So this is a Strock-Osborne mechanism, let's say. Without coordination with the metal center, this is not happening. If a chloride is there or a other counter anion is there, this coordination becomes difficult, very difficult. Okay, both electronically as well as sterically. Okay.
Okay.
Okay. Hopefully that answer your query. Do you have any other question at this point?
No, it's fine.
It's fine. Okay. So I will move on to another related but different chapter, and that is the hydroformylation reactions. Okay. Let's see. Let's share the slide. Okay. Can you see my slides now? Can you see my slides?
Yes.
Okay.
Yes.
Good, good. So once again, we are discussing on a similar banner as we were discussing the hydrogenation reaction. The reaction mechanism will be strikingly similar, very similar. Of course, hydroformylation is a little bit different than the hydrogenation reactions. I will briefly discuss for this class. Okay. So what are the reactions we are looking at? We are looking at, this is again very briefly we have mentioned at the very beginning of this course. So we have, these are the reactions truly industrial scale. You don't have to worry about the amount of product formation. These are happening really, metric ton, 100 kg scale, 1000 kilo scale, also whatever scale you want to do, people are doing in industry. So, effectiveness of these catalysts are unquestionable. So you take olefin, you take hydrogen and CO. There are two product formation likely. One is the aldehyde, okay, linear aldehyde, or another would be the branch product formation. Okay, so linear or branch product formations are possible. Just a second. So what we see is two different type of product formations. Either it's a linear product or a branch product. But all of them or both of them has a formyl group. So HCO and H, these are the formyl group. HCO and H is over here. These are the formyl group, that is, sorry, not this one, over here. Okay, these both of the cases, it's the formyl group that is adding. So what is adding here? This aldehyde group and a hydrogen over here. Similarly, formyl group and a hydrogen over here is happening, right? Produces aldehyde from alkene via addition of a CO or hydrogen to alkene. Okay, so this is the hydroformylation reaction. The mechanism right away. This is a cobalt carbonyl complex. Okay, we see a cobalt carbonyl complex, CO2CO8, HCOCO4 and HCOCO3. What is happening here? You add a hydrogen to a cobalt carbonyl complex, you form a hydrido-cobalt carbonyl complex, and from there one CO goes out, another CO, and you form a very reactive intermediate, HCOCO3. So this is the reactive catalyst. This is the starting material, as the top one is the starting material, and the reactive or the main catalyst is this HCOCO3, and subsequently olefin coordination happens and it gives to the hydridoalkyl species, right? So once again, olefin coordination is same, reactive intermediate formation is similar as you have seen in hydrogenation reaction. You have to lose a ligand, you have to do some initial rearrangement or initial reactions to get a HCOCO3 intermediate. Subsequently, this olefin coordination comes into picture, and the hydride also comes into picture. This hydride inserts into olefin, subsequently. Now, where hydride is inserting, that is the point, right? So hydride can insert at here or hydride can insert over there. If hydride is inserting over the terminal position, okay, this is the terminal position, right? If that is happening over here, that is what you call it the so-called Markovnikov addition, right? If hydride is transferring over here, then you will get the branch product. But if hydride is attaching at these positions, right, at the internal positions where less hydrogen is there or more bulky substituents are there, that is anti-Markovnikov addition, and then the corresponding carbonyl complex is happening at the terminal position. But as you know, these two intermediates, so whether this hydride transfer occurring at the branched or at the terminal or an internal position will dictate the linear or branch product formation as you see from here. So this intermediate, which is going to be the linear product formation intermediate, is the primary alkyl intermediate, whereas this one is the secondary intermediate. Okay, so this linear intermediate is required for the reductive elimination. Okay, for the reductive elimination to form the linear product. So this pathway, as you see over here, mainly goes to the linear product. Okay, the steps are same, right? I'll walk you through very quickly, very simply once more. What is happening here is the reactive species formation that you have olefin coordinates, just like hydrogenation, olefin coordinates. As you have seen in hydrogenation also, you have hydride. Okay, hydride can attach over here or hydride in attach over there. In hydrogenation reaction, it did not really matter, or we did not discuss, because both the reductive elimination step and beta migratory insertion step are having hydrogen. So it doesn't really matter whether hydride is adding at the terminal place or in the internal place. But in this case, it matters whether hydride goes to, let's say, A or hydride goes to B, because the A would be leading to hydride, the branched product, right? This is going to be branched product, and this mode of addition is going to be linear product formation, right? So this matters a lot now. All of a sudden, the mode of hydride insertion or beta migratory insertion becomes very, very critical. What we then have is an opportunity, either you get a linear product formation or a branch product formation. Linear product formation is going to be the one where you get a primary alkyl intermediate. You have to spend a little bit time looking at these intermediates. So this is the primary alkyl intermediate. No substituent is there at this carbon. On the other hand, this carbon center, you see there is a substituent. This is a secondary or 2-degree alkyl intermediate. This is primary. So primary alkyl species versus secondary alkyl species. Primary alkyl species will lead to the linear product. Secondary alkyl species will lead to the branched product formation. Of course, it could be a problem. If you have both the product formation is happening, that's a big problem. So you need to have a catalyst which will give you only one product, either linear product or branch product, preferably the one you are looking for. So depending on that, what you want, you can actually dictate what is the reaction that you do. Okay. Okay. So depending on this, we'll see what is going on over there. There is a background noise coming. Okay. Okay. Sure. If Martha, if you have a question, you can ask. Do you have a question?
Yeah. Yeah. So for the separation, for 1 degree or 2, like branched or linear, so it's a boiling point, melting point, or any other like chemical process we use for the separation of both the column or
no, this is going to be tricky. This is going to be very difficult. Well, of course, column chromatography could be one of the way, but usually you don't isolate these intermediate. Any of the catalytic cycle intermediate, you don't isolate. You let the reaction go.
Yeah.
Once you have the products, then you try to deal with the products, not with the intermediate. Okay. So if you go back, so these two products, these are organic product. If you have these both the product formation, once you have the problem, then you deal with the problem. Otherwise, you try to do 100% of these, let's say, or 0% of that. So you try to find a catalyst which will give you 100 and 0. If there is a mixture, often it could be, let's say, 98% of these and 2% of these. Well, then you deal with it, right? In industrially, you deal with one different way, and academically you do different way. So you have to deal with it. Otherwise, so this is the choice of catalyst. That's why it becomes very, very critical. We want to get a catalyst which gives as close as 100% product formation as possible. Either way, if you need this product, you want to have one catalyst. If you need this product, you would like to have another catalyst. Okay. Well, this is why we need to also understand when or what type of catalyst gives you linear product and what types of catalyst gives you branch product, and then what type of modification you want to do to get linear versus branch product, one versus another, if possible, exclusively 100%. Well, this is a real problem actually, getting exclusive linear product and branch product. For the easier starting material, of course, it would depend on the catalyst, and also it will depend on the olefin, right? Quite a lot of olefin might will give only one product, but then there are many other olefin which will give the mixture of products. And this is where the controlling the ligand on the metal center becomes very critical. Okay, we'll discuss those little bit. So ligand coordination with the metal center becomes critical. In these cases, as you see, these are all basically carbonyl. Not much control is there, right? Exactly carbonyl. There is no phosphine or pyridine or other ligand, carbene or phosphine other ligand. So their control is not too much. Okay. But when you displace one of the carbonyl with, let's say, one of the phosphine, then you can start controlling the mode of addition, whether it goes for linear product, means a primary alkyl versus a secondary alkyl. Then you can try to dictate. Okay. So this is where, of course, a lot of research has been done, how to control this sort of selectivity. Another most important part is for this type of chemistry. In this case, of course, there is no asymmetric center, right? This is a linear simple product. But in this case, you can generate a stereo center right over here, right? It could be R or S, stereo center, right? So asymmetric molecule or enantiomer pure molecule synthesis by this method is an excellent opportunity. Okay, and this is truly exciting domain. Once again, in industry, people try to do it in as many cases as possible, because you see the starting materials are very cheap. If you look at aldehyde, you can convert aldehyde into many other functional group, right? Almost every functional group you can convert. That means that if you can do an asymmetric synthesis like this, as you see in here, at this step, if you can do an asymmetric synthesis and generate the stereo center or control the stereo center at the hydroformylation level, that's going to be fantastic. That's going to be truly important in many synthetic synthesis. It could be your natural product synthesis, it could be many pharmaceuticals, agrochemicals, and many other simple synthesis, maybe 2-step, 3-step, or even 15-step, doesn't really matter how many steps, but this step can control the stereo selectivity. Anyway, moving on. So the secondary alkyl group, as I was discussing, will control the secondary secondary alkyl pattern will lead to the branch product formation. This is leading to the branch product formation, and this is leading to the linear product formation. The mechanism, as I said, and you can understand that it's very simple: olefin coordination, beta migratory insertion. So why it is beta migratory insertion? With respect to the metal center, the hydride that adds, this hydride is really that hydride. This hydride is that at the beta position. So this hydride is this hydride. Okay, again, this shaded hydride is the hydride over there. Okay, this hydride. So the hydride is adding at the beta position. Okay, so as you can see over here, the beta hydride or the hydride over here, this is the hydride is coming from there. And this is a primary alkyl group. This is a secondary alkyl group. As I discussed earlier briefly, that primary alkyl is more stable because it is steric crowding around the metal center is least. So this sort of metal complex will give you the primary alkyl intermediate leading to the linear product. After this, CO, this is you are doing in CO and hydrogen pressure. CO and hydrogen pressure, of course, olefin is also under pressure. So CO and hydrogen pressure, CO gets in and CO gets in this metal alkyl bond. So this metal alkyl bond is getting the CO. So alpha migratory insertion. So insertion happens, one of this CO, which is here, insertion happens from here. Of course, CO from outside can join in. So CO3, the cobalt tris carbonyl, that remains same, CO3. Cobalt tris carbonyl remains same, right? Cobalt tris carbonyl remains same. And this alkyl group, which was over here, it is now having an alpha migratory insertion from CO. Okay, then an oxidative addition into this. So you see the oxidative addition into this to give you this intermediate where the hydrogen oxidative addition actually happening at this stage. So for olefin coordination, beta migratory insertion, alpha migratory insertion, and then oxidative addition is happening. Finally, reductive elimination, H and one of this partner, this whole thing is really participating to give you the product. Okay, if you just take a deep breathe and you will see everything, literally everything you can see is here. This is a ligand dissociation, olefin coordination, beta migratory insertion, alpha migratory insertion, oxidative addition into hydrogen, and then reductive elimination, right? So this is truly exciting to know that all these things are happening quite effectively in this process. Okay, so what again what I was trying to tell, that you have olefin coordination, beta migratory insertion, as well as alpha migratory insertion, hydrogen oxidative addition, and reductive elimination. All the key steps, as well as ligand dissociation, all the key steps are involved in there. So in a way, if you understand the hydroformylation reaction, a majority of the homogeneous catalysis mechanism, you can understand pretty easily, right? And also you have the complexity of the primary versus a secondary alkyl group, right? This is a beautiful mechanism and simple mechanism, beautiful mechanism, and it works quite efficiently. As I said, industrially, it is very important process. Now, another important thing is, in terms of industrial importance, this is truly innovative and exciting. This is a very old reaction as well. And the importance coming from the fact that this one alkyne, or one alkene, sorry, in these cases, which is very readily available. These are petrochemical industry material, right? One alkene, if you can convert into something useful such as aldehyde, that's very important, because these are feedstock, readily available materials, right? Readily available material, cheap material, and you are converting into, just by using hydrogen and CO, you are converting into aldehyde. So these are truly groundbreaking reactions. Okay, and production of plastics, of course, is dependent on this hydroformylation reaction. This is the key step for the production of plastic as well, and industrially useful compounds are produced quite a lot by hydroformylation reaction, as I was trying to impress upon you. Long carbon chain alcohol, because these aldehydes you can reduce to alcohol, right? If you get a long chain aldehyde, you reduce it, hydrogenate it, you get alcohol, which is basically detergent. Many uses you need, right? You can imagine the world supply of detergent, how much detergent we need, and these different surfactants, different component of detergent, and many other, almost every reaction that you can think of, or every materials that we need, it can be interconverted through the aldehyde, right? So this is an aldehyde synthesis, even the aliphatic aldehyde synthesis, which is fantastic. Anyway, the most often usage or most often important species is this cobalt, this HCOCO4, which is from the CO2 CO8, it is prepared. And then there is other catalysts such as this phosphine catalyst, which is quite important and critical. And we can also have different other rhodium-based catalysts, hydrid rhodium monohydride catalyst that you have seen before. And of course, aqueous phase rhodium catalyst can also be coming into the picture. Depending on the need and usage, you can have different variation of these catalysts. As you see, cobalt or rhodium catalysts are the ones which are predominantly used for these sort of hydroformylation reactions. Okay, so just a quick comparison, when or what is the benefit of these two different rhodium catalyst. Okay, so this is the readily available cobalt catalyst, HCO4, as you have seen from the cobalt, CO2 CO8, which is like really cheap material. You can prepare this. This is the oldest homogeneous catalyst, and still it is in use industrially. In industry, what happens once you have a good method and it is optimized, industry doesn't want to change it, because any change would lead to a lot of change in engineering, product supply line, starting material, and the processing. So if some catalyst is working well, let's say 50 years old thing or old reaction, if it is working really well, industry has reluctance to modify it, and that is for good reason, because any modification will lead to huge financial burden or financial difficulties, right? You don't know how effective it would be. A new one, it will be in a complex situation, right? So the old catalysts are usually trusted quite well in the industry. So hydrogen and CO is mixed usually in 1:1 ratio. Pressure is high, 200 to 300 bar. All for industry, these are done quite regularly, and they are pretty well equipped and well managed. But in academic labs, sometimes very high pressure is a problem if the setup is not really very steady. In industry, the high pressure reaction is not that much of an issue compared to the academic group. Depending on the group, of course, research group, sometimes doing high pressure reaction becomes a difficult thing if there is no suitable apparatus available, right? So nonetheless, so in these cases, linear is to branch products are 4:1, which is pretty difficult or problematic, I would say. And the cobalt at high temperature and low pressure, it decomposes. This catalyst decomposes at high temperature and low pressure, right? That's one of the big drawback you have for this sort of catalyst, but in a number of cases, it is still used. Well, when you introduce a PR3 in place of one of those cobalt, so what you are seeing here is one of the cobalt, one of the carbon monoxide is replaced by phosphine, right? When you replaced one of the carbon monoxide with phosphine, the addition of PR3 ligand causes a dramatic change in rate and regioselectivity due to electronic and steric effect of substituent. So this phosphine ligand makes the game completely different. Here you don't have any control, right? Any control on things, because these are carbonyl. I mean, you cannot have a derivatives of carbonyl. On the other hand, phosphine, you can have many different phosphine. You can have, just theoretically speaking, trimethyl phosphine if required, pH3 phosphine itself, or even triaryl phosphine, different sort of aryl phosphine, trialkyl phosphine, different sort of alkyl phosphine you can have. So electronic effect of PR3 group, because you can vary the PR3 group, you can vary the R group quite a lot, right? In the CO, you are dead end. You have nothing to vary. So this stronger cobalt carbonyl bond actually is not decomposing, right? Stronger cobalt carbonyl species do not decompose. That makes it very, very stable. So if you have a phosphine compound, previously what was happening, if you have this tetracarbonyl compound, these decomposes under high pressure, under high temperature or low pressure, because CO will come off. But with the phosphine, this becomes really, really good. And the phosphine being electron donating, phosphine is electron donating the other CO bond. So in this case, for example, these COs are not that very strong, but phosphine being electron donating, this back bonding becomes stronger. Back bonding becomes stronger, right? That means this will now be a stabler complex, more stable complex, and hydride also will be more nucleophilic compared to this hydride, right? That makes sense. That's an excellent opportunity. So less active, of course, it would not be too much active, 5 times slower in terms of olefin binding and all other steps, but hydridic characteristic of hydride increases the hydrogenation capability, okay? So although the overall in the catalytic sense, this phosphine compound is a little bit less active than the tetracarbonyl one, but it becomes quite useful because the stability increases, hydridic activity, the hydride insertion, hydridic activity increases. So the bulky PR3 group influence the insertion reaction direction of alkene to CO complex, and geometry, of course, it favors anti-Marconic of that I was talking about, and then the linear product formation becomes really easier or better, okay? That is what we are looking for in the first place, like linear product formation. So what I'm saying here, it is in here. Previously, as you can see, in these cases, you get with tetracarbonyl, okay, with the tetracarbonyl, you get 4:1, 4:1 selectivity for linear is to branch, right? 4:1. That is really a not so great ratio. Of course, this is a problem, linear is to branch product. But the moment you introduce a phosphine ligand, what happens? Phosphine is donating. Here, everything was withdrawing. Everything was withdrawing. Everything need a back donation, right? Synergistic effect. Everything need a back donation. Here, phosphine is predominantly donating, and then these are stable bond. Although this is little bit less reactive, but the selectivity becomes much of much of an improvement, because this hydridic character increases quite efficiently. So the linear product formation increases dramatically. Okay, so now you have actually 9:1, from 4:1 to 9:1 selectivity, depending on what R group you are using. With this tributyl phosphine, you have 9:1 selectivity. That is because this hydride addition, okay, so this hydride adds to this center pretty easily, because this is a more of a hydride, better hydride, I would say, and then the linear or the primary alkyl intermediate forms is quite effectively, right? And this is where we see that this is going to be a quite an important reactions. Okay, we'll stop over here. Better, as this is better as compared to the previous catalyst. So we stop here today, and we'll see you soon in the next class. Thank you very much. Hi, Mamta. Yeah, you are also in the class. Sorry. Yes. Yeah. Yeah. So do you have any question that we can discuss, or we can come back in 10 minutes?
Yeah, we can come back in 10 minutes.
10 minutes, 10 minutes. So let's say maximum 12 minutes or so. 5:30, let's we meet.
Okay, fine.
Okay, 5:30, exactly at 5:30 we will meet. Okay, thank you very much. Okay.
Thank you.